Hello students, in today's lecture we will see points from thermodynamics. First point is changes in internal energy and temperature dependence of internal energy. And second point is the variation of enthalpy with temperature. So our first point is changes in internal energy and temperature dependence of internal energy. So, we will begin to unfold the consequences of change in internal energy, that is du, being an exact differential by exploring a closed system of constant composition. And the internal energy U can be regarded as a function of Vt and P. That is, V means volume, T means temperature, and P means pressure. But because there is an equation of state stating the values of two of the variables fixes the value of the third. Therefore, it is possible to write U in terms of just two independent variables, V and T or P and T. Internal energy is dependent upon volume, temperature and pressure, but we can write only two variables. One is constant and second is varying. So we can write V and T or P and T or P and V. That means volume and temperature, this is one pair, pressure and temperature, this is second pair, and pressure and volume, this is third pair. Expressing internal energy U as a function of volume and temperature fits the purpose of our discussion of today's lecture. So we will see how internal energy is related to volume and temperature. So we will see the internal energy change, that is a du, and the internal energy is a function of the volume and the temperature. When these two quantities are going to change, the internal energy changes by equation du is equal to del u divided by del v at constant temperature into dv plus du or del u divided by del t at constant volume into dt. So here del u represents the change in internal energy with respect to change in volume at constant temperature, and here the change in internal energy with respect to change in temperature at constant volume. So this equation represents the two quantities are going to change, either volume or temperature. Any one is constant and one is changing. And this equation is known as the general expression for a change in internal energy U with respect to temperature and volume. And the interpretation of this equation is that in a closed system of constant composition, any infinitesimal change in the internal energy is proportional to the infinitesimal changes of volume and temperature. The coefficients of proportionality being the two partial derivatives. So we will see a next diagram which shows the variation of internal energy with respect to temperature and volume. So see, this is the diagram. On y-axis there is the internal energy and on the x-axis there is the temperature. An overall change in internal energy U, which is denoted by du, arises when both volume and temperature are allowed to change. If second order infinitesimals are ignored, the overall change is the sum of changes for each variable separately. So see, here on the y-axis the internal energy changes, and on the x-axis there is a change in temperature and volume is here. So the equation at this point is given here. U plus del U divided by del V at constant temperature into dV plus del U divided by del T at constant volume into dt. So this is the equation which shows the change in volume and temperature is allowed, and that time we can measure the change in internal energy by using this equation. Now the next term is the internal pressure. Here, in many cases, partial derivatives have a straightforward physical interpretation, and thermodynamics gets shapeless and difficult only when the interpretation is not kept in sight. In the present case, we have already met del U divided by dt at a constant volume. That is this equation. Here, internal energy is changing, and here the temperature is changing, and the intersection is here. That means we made to this point del U by dt at constant volume, where we saw that it is the constant volume heat capacity, that is Cv. So equation du by dt at constant volume represents the heat capacity. We have seen the definition of heat capacity in previous lecture. So this is the formula of constant volume heat capacity, or the heat capacity at constant volume, that is del U divided by del T at constant volume. So we can represent this equation by Cv, and the other coefficient del U divided by del V at constant temperature. This plays a major role in the thermodynamics because it is a measure of the variation of the internal energy of a substance as its volume is changed at constant temperature, and we shall denote it as a pi t. And because it has the same dimensions as the pressure, we shall denote it pi t, and because it has the dimension of pressure and it arises from the interactions between the molecules within the sample, and we can say that this is the internal pressure pi t. So pi t is defined as du by dv at constant temperature. So above equation, at which the equation is given du by dt at a constant volume, this is we can represent by Cv. So here plus Cv dt, we can write this equation as plus Cv dt, because this is the definition of constant heat capacity at a volume or at a constant volume. So we can define the new term, the constant heat capacity Cv, as a du by dt at constant volume, and now we can write the equation for the internal pressure. So equation for internal pressure is here. As I have told, pi t represents the internal pressure, and internal pressure is equal to du by dv at constant temperature. So we know the molar heat capacity at constant volume is du by dt at constant volume, but here there is a change. One is varying and one is constant. So here internal energy is changing with respect to change in volume, and temperature is constant. So this term is known as internal pressure, and this is denoted in the next diagram. So the internal pressure change is given here. On the y-axis there is the internal energy U, and here is the temperature, and here is the volume. So system is represented by x, y, z, and see here is a plot, and in this plot the slope is the pi t. So see, the heading of the diagram is the internal pressure pi t. Here pi t is given. So internal pressure pi t is the slope of U with respect to V with the temperature T held constant. So see, here is the plot. U with respect to volume and when the temperature is constant. And when we take a slope of this graph, this is a curve, and here we have taken a slope, and this slope is equal to pi t, that is internal pressure. Now this is the next diagram which shows the internal energy is independent of the volume. If we have taken molecules of real gases, the internal energy increases with the volume. This is because of the molecules become further apart on average, and there are the repulsions, and when the repulsions are dominant, the internal energy decreases as gas is going to expand. And in terms of the notation Cv and pi t, we can write the equation number 1 as again. The equation number 1 is du is equal to, see here is our equation number 1. du is equal to du by dv at constant temperature into dv plus du by dt at constant volume into dt. So du by dt at constant volume, we have seen this is the definition of heat capacity at constant volume. So we can write here Cv. And now we have seen next definition, du by dv at constant temperature is equal to pi t. So instead of this we can write pi t. So our equation 1 can be written as du is equal to pi t into dv plus Cv dt. So pi t dv plus Cv dt, this is our third equation. And when there are no interactions between the molecules, the internal energy is independent of the molecule separation and hence independent of the volume of the sample. And therefore a perfect gas, we can write the change in internal pressure is equal to 0, that is pi t is equal to 0. And the statement pi t is equal to 0 can be taken to be the definition of a perfect gas. Now the equation can be written as du by dt at constant pressure is equal to pi t into dv by dt at constant pressure plus Cv. So just equation is written when the pressure is constant, or the change in internal energy at constant pressure is given by equation du by dt at constant pressure is equal to pi t in bracket dv by dt at constant pressure plus Cv. So the next change in internal energy is the changes in internal energy at constant pressure, and this is given by this equation. This we have seen the changes in internal energy with respect to temperature and volume, and in this equation we have seen the changes in internal energy at constant pressure. So this is the all over the changes in internal energy at pressure and temperature. This will be either pressure is constant or temperature is constant. So till here the temperature is constant, and this equation is used when the pressure is constant to find out change in internal energy. Now we will see the variation of enthalpy with temperature. So here again heat capacity at constant pressure is the first point for finding the variation of enthalpy with temperature, and our next point is here the relationship between heat capacities. So see, we will see from this heat capacity at constant pressure. So see, heat capacity at constant pressure is given by equation Cp, and heat capacity at constant volume is given by equation Cv. And now we have seen the definition of heat capacity at constant volume. du by dt at constant volume. This is the equation of Cv, and Cp means du by dt at constant pressure, or Cp can be defined as dH by dt at constant pressure, or this is known as heat capacity at constant pressure. So in today's lecture we have seen the changes in internal energy with respect to temperature, and now we will see the changes in the enthalpy with respect to temperature. So see, the definition is written here: Cp is equal to dH by dt at constant pressure. So for infinitesimal changes of temperature, the equation can be written as, just transfer this to the left side. dH is equal to Cp into dt. This is the equation at the constant pressure. Now the plot is here, which shows the change in enthalpy with respect to change in temperature, and we can find out the internal energy. So plot is of H versus T, and the slope is U. So the constant pressure heat capacity at a particular temperature is the slope of tangent to a curve of enthalpy of a system plotted against temperature and when the constant is pressure. For gases at a given temperature, the slope of enthalpy versus temperature is steeper than that of the internal energy versus temperature, and CPM is larger than CVM. That means molar heat capacity at constant pressure is greater than the molar heat capacity at constant volume. So from this plot H versus T, we can find out internal energy from this tangent. Now if the heat capacity is constant all over the range of temperatures of interest, then for a measurable increase in temperature, the enthalpy is given by equation delta H is equal to integration of Cp dt. Here temperature is changing, that's why integration is taken, and integration with respect to limits T1 to T2. So Cp is taken common, and in the integration only dt is there. So you can write dt integration in terms of delta t, and delta represent the change. That's why the final value minus initial value, that is t2 minus t1. So del h is equal to Cp into delta T, or T2 minus T1, and we know that delta H is equal to Q, that is heat is equal to change in enthalpy. So you can write the Q at constant pressure, or heat at constant pressure, is equal to Cp into delta T. And this is because a change in enthalpy can be equated with the energy supplied as heat at constant pressure. And this expression shows us how to measure the heat capacity of a sample. A measured quantity of energy is supplied as a heat under conditions of constant pressure, and the temperature rises as monitored, and the variation of heat capacity with temperature can sometimes be ignored if the temperature range is small. This approximation is highly accurate for a monoatomic perfect gas. However, it is necessary to take the variation into account. A convenient approximate empirical expression is CPM is equal to A plus BT plus C by T square. So, CPM represents the molar heat capacity at constant pressure. A and B are the constant, T is the temperature, A, B, C are the constant. So, the empirical parameters A, B and C are independent of temperature and are found by fitting this expression to the experimental data. And The next type or the next is the relationship between heat capacities. So most systems are expanded and this is due to there is a heat. So system is heated at a constant pressure and such systems do work on the surroundings and therefore some of the energy supplied to them as a heat escapes back to the surroundings. As a result, the temperature of the system rises less than when the heating occurs at constant volume, and the smaller increase in temperature implies a larger heat capacity. So, as the temperature increases, obviously heat capacity will increase. So, we conclude that in most cases, the heat capacity at constant pressure of a system is larger than its heat capacity at constant volume. And there is a relation which shows the relationship between two heat capacities of a perfect gas, that is Cp minus Cv is equal to Nr. Cp represents the molar heat capacity at constant pressure, Cv represents the heat capacity at constant volume, N represents the number of moles, and R is the molar gas constant. So the heat capacity of a perfect gas is about 8 joule per Kelvin per mole, which is larger at constant pressure than at constant volume. So this is all about the internal energy and the enthalpy.